In a basement in Cleveland, a machine was built to notice a movement that no human body could feel. The room itself seemed almost still. Stone rested on liquid mercury. Mirrors waited in careful alignment. A beam of light entered the apparatus, divided into two paths, reflected back, and joined again in a pattern of pale brightness and shadow. To anyone passing by, if they could have seen it at all, the scene might have looked too quiet to matter. But the question inside that quiet room was enormous. Albert Michelson and Edward Morley were trying to detect the Earth's motion through an invisible medium that many physicists believed filled all of space. This medium was called the luminiferous ether. If light was a wave, and if waves needed something to travel through, then perhaps light moved through this hidden substance as the Earth sailed through it. The planet was orbiting and moving through the heavens. Somewhere, somehow, that motion should have left a mark. The mark they wanted was not a flash or a sound. It was a tiny shift in a pattern of light so small that only a precise instrument could reveal it. If the expected shift appeared, it would show that the Earth was moving through the invisible ocean that carried light across the universe. But the expected shift did not appear. At first, that might seem like a failure. The experiment had searched for a sign and did not find it. Yet the deeper story of science often begins in such moments when a careful question is answered in a way no one wanted. And the answer is not a discovery, but a refusal. This is the story of the Michelson-Morley experiment, one of the most famous negative results in the history of physics. It is a story about light, ether, precision, patience, and the strange power of a result that seemed to say almost nothing. How can an experiment change science? By failing to find what it was built to find. And what happens when the universe does not leave the trace that human reason expected? In the summer of 1887, beneath the ordinary life of a university building in Cleveland, a room was prepared for a test of almost impossible delicacy. It was not a theatrical place. There was no crowd gathered around a platform, no machine roaring into motion, no great telescope opened toward the stars. The experiment was set closer to the ground in a basement where the air could be steadier and the vibrations of the outside world could be reduced. The room mattered because the effect being sought was small enough to be hidden by the slightest disturbance. Inside, the materials were plain and strangely beautiful. There was stone, glass, metal mirrors, and light. A large slab of sandstone carried the delicate parts of the apparatus. Beneath the stone was mercury, heavy and liquid, allowing the slab to float and rotate with unusual smoothness. The arrangement looked less like a dramatic machine than a carefully balanced question. Albert Michelson and Edward Morley were not trying to discover a new planet or isolate a new chemical element. They were trying to catch a trace of motion. If the Earth was traveling through a hidden medium called the ether, then light moving in different directions should reveal a tiny difference. The task was to build an instrument sensitive enough to notice that difference before the noise of the world buried it. The instrument they used was an interferometer. Its logic was elegant. A beam of light entered the device and was split into two beams. One traveled one way, the other traveled at a right angle. Each beam reached a mirror, returned, and met the other again. When the two beams reunited, they formed a pattern of alternating light and dark bands. Those bands were the key. They were called interference fringes, and they carried information about the two journeys of the beams. If one beam took even slightly longer than the other, the waves would meet differently and the pattern would shift. A tiny difference in the travel time of light too small for ordinary measurement could appear as a movement in the bands. The experiment was not trying to see ether directly. No one expected the invisible medium to appear as a mist or a glow. The test was more subtle. It asked whether the Earth's motion through the ether would alter the timing of light in one direction compared with light in another. To understand why this mattered, it helps to remember that the Earth was not still. It spun on its axis. It moved around the sun. The solar system itself moved through a larger cosmic setting. If space was filled with a medium through which light traveled, then the Earth should have been moving through that medium. That motion should have had consequences. Michelson and Morley's apparatus turned slowly so that its two light paths could face different directions relative to the supposed ether wind. In one orientation, one arm of the instrument might align more closely with the Earth's motion through ether. In another orientation, the arms would exchange roles. If the ether wind existed in the expected way, the interference pattern should change as the instrument rotated. The room therefore became a small test chamber for a cosmic question. Nothing about the basement looked cosmic. The stone was local. The mercury was local. The mirrors were fixed by human hands. The observers looked through their instrument and recorded small optical details. Yet the question reached beyond the building, beyond the city, beyond the Earth itself. Was the planet moving through an invisible sea of light? There was another quiet tension inside the room, one that had nothing to do with noise or vibration. It came from the fact that the experiment was being performed on the very object whose motion it was trying to detect. The Earth was the platform. The laboratory was attached to it. The instrument, the stone, the mercury, the mirrors, and the observers were all being carried along together. This made the question strangely intimate. Michelson and Morley were not watching Earth from some distant point in space. They were not standing outside the planet with a cosmic ruler. They were inside the moving system, trying to detect motion from within. Their machine had to reveal what their bodies could not feel, what the walls could not show, and what ordinary experience concealed. In daily life, the Earth gives us a powerful illusion of rest. A table stays where it is. A lamp remains on a desk. A basement floor feels solid under the feet. Nothing in the senses announces that the whole room is turning with the planet and circling the sun. We learn this motion intellectually through astronomy and mathematics, but we do not feel it as we feel wind on the face or water against the hand. The Michelson-Morley experiment lived inside that gap between knowledge and sensation. Astronomy said the Earth was moving. Ether theory suggested that movement through the medium of light should have consequences. But human perception said the room was still. The instrument was built to settle the dispute, not by appealing to intuition, but by letting light compare one direction with another. That is why the experiment feels almost meditative. It does not begin with a dramatic act. It begins with discipline. Remove vibration. Stabilize the apparatus. Align the mirrors. Let the light travel. Turn the stone. Watch the pattern. Repeat. Somewhere in that repetition, if the old picture was correct, the hidden motion of the planet should become visible. This is a very different kind of grandeur from the grandeur of a mountain or a storm. It is the grandeur of smallness handled with care. A tiny shift in a pattern of light was being asked to carry the meaning of Earth's movement through the universe. The basement was ordinary only in scale. In function, it had become a crossroads between the human and the cosmic. A person could stand there and see only a room. But the experiment treated the room as part of a moving astronomical body. It turned a quiet interior into a test of the relation between Earth light and space itself. That is why the missing result would later feel so strange. The experiment was not carelessly looking for wonder. It had taken a large, serious idea and given it one of the most careful tests available at the time. The ether was not being mocked. It was being granted an opportunity to appear. And when a serious opportunity is given, failure becomes meaningful. For the test to mean anything, the room had to be controlled. Every tremor mattered. A vibration in the floor could disturb the pattern. A shift in temperature could alter the apparatus. A movement too small to notice in ordinary life could imitate or hide the effect they were looking for. In a normal room, stillness is a feeling. In this experiment, stillness had to be engineered. That is why the floating stone is so important. It gave the apparatus weight and steadiness, while the mercury allowed it to turn. The design brought together two opposite qualities: resistance to disturbance and freedom of rotation. The stone held the instrument with the patience of the earth itself. The mercury allowed the question to be asked from one direction, then another, then another. There is a quiet poetry in that, though the scientists were not building poetry, they were building control. Michelson had already pursued the problem before. He had tried an earlier version of the experiment, and the results had not provided the expected evidence for ether drift. The later collaboration with Morley improved the design and made the Cleveland experiment more stable and refined. It was a second, more careful attempt to make the invisible measurable. The expectation was not vague. If the Earth moved through ether, the apparatus should show a shift. Not a large one, and not one that would startle anyone standing in the room, but a measurable one. A small displacement of the fringes would have been enough to say that the hidden medium had left its mark. The observers watched for that displacement. The machine turned. The beams traveled out and back. The pattern appeared. The instrument was rotated again. The Earth continued moving through space, carrying the room, the apparatus, and the men inside it. The expected sign did not come. At first, this is a difficult kind of event to hold in the mind. Human beings are drawn toward moments when something appears, a spark, a color change, a mark on a plate, a new object in a telescope. Here, the important thing was a movement that should have appeared but did not. The experiment did not produce a spectacular signal. It produced a disciplined failure of expectation. That is different from mere failure. A careless experiment can fail and teach little. An instrument too crude for the task can fail because it was never capable of success. But a precise experiment that does not find what a theory predicts creates a more serious problem. It does not merely leave the question unanswered. It begins to question the assumptions behind the question. For Michelson and Morley, the immediate conclusion had to remain careful. They had not detected the expected relative motion of the Earth through the luminiferous ether. That was already enough. The experiment had asked nature for a certain sign, and the sign had not appeared in the predicted way. The larger meaning would take time. No one stepped out of the basement already living in Einstein's universe. The old physics did not collapse in a single afternoon. The ether did not vanish from every mind because one pattern failed to move as expected. Scientific change is usually slower and more complicated than later stories make it seem, but the result could not be ignored. The more carefully the apparatus had been made, the more weight its result carried. The silence of a sloppy instrument would have meant little. The silence of this instrument meant something more troubling. It had been built precisely to reveal a difference, if the difference existed in the expected form. The experiment became powerful because it was careful. It resisted the expectation that ether would reveal itself through light's travel time. It resisted the familiar picture of the Earth moving through a hidden medium like a ship through water or a body through air. It resisted the comfort of a universe where every wave could be explained by imagining a substance beneath it. And yet it did not give an easy replacement. That is the unusual tension of the room in Cleveland. The experiment did not say in one clean sentence what the universe was. It said that something important had not appeared. It left physics with a missing trace, and the missing trace became a fact that future theory had to carry. Imagine the apparatus once more. The beam enters, it divides. Two paths open inside the machine. The mirrors return the light. The fringes form. The stone turns gently on Mercury, carrying the optical system through new orientations. The observers look for a slight shift that would connect the basement to the movement of the Earth through an invisible cosmic medium. The shift is not there. Outside, the planet continues through space. Inside, the pattern remains far too still. This is where the story begins to deepen. The most important thing in the room is not a discovery that appears, but an expectation that fails to appear. The machine does not reveal the ether wind. It reveals a problem. For a sleep documentary, the moment is quiet enough to rest inside. There is no need to rush. The light can travel again and again. The stone can turn. The mercury can hold its silver surface. The room can remain still in the human sense, while the earth moves in the astronomical sense. The contradiction is gentle, but it is profound. A basement built to catch motion found almost none of the motion it was looking for. A device made to confirm the hidden ocean of light, instead, left that ocean harder to believe in its old form. The result was not yet a revolution, but it was no longer ordinary disappointment. It was the beginning of a question that would outgrow the room. To understand why that question mattered so deeply, we must leave the basement for a while and return to the older idea that made the experiment necessary. Before anyone could be disturbed by the missing ether wind, they had to believe there was an ether wind to find. Before the machine could threaten an invisible ocean, the ocean itself had to seem real. Why did so many careful minds think light needed such a sea? Before the basement in Cleveland could become a place of mystery, the invisible thing Michelson and Morley were searching for had to become believable. That is where the story must slow down. The ether was not born from foolishness. It was not a superstition clinging to the edge of modern science. To many physicists of the 19th century, it seemed like a reasonable answer to a difficult question. Light traveled across space. It came from the sun, from stars, from lamps, from flames, from heated metal, from lightning, from every visible surface, reflecting or emitting it. It could be bent, reflected, split, and studied. By the 19th century, the wave theory of light had become powerful, especially because light could produce interference and diffraction effects that made deep sense when light was treated as a wave. But waves in ordinary experience need something to wave through. A ripple on a pond is not an abstract pattern floating by itself. It is water moving. A sound in a room is not simply a message. It is air being compressed and released, carrying vibration through the space between source and ear. A wave on a rope exists because the rope itself bends, rises, falls, and transmits motion. So when light behaved like a wave, the natural question followed. What was waving? This question had great force because light crossed regions where ordinary matter seemed absent. Sunlight traveled across the space between sun and earth. Starlight crossed distances so vast that they were already difficult to imagine. If light was a wave, and if waves needed a medium, then the medium could not be limited to air or water or glass. It had to fill the heavens. The name given to this imagined medium was the luminiferous ether, the light-bearing ether. The phrase sounds old now, almost dreamlike, but in its own time, it belonged to serious thought. The ether was imagined as transparent because light passed through it. It had to be nearly weightless because planets did not slow as they moved through space. It had to be everywhere because light arrived from every direction. It had to be subtle enough to pass through matter, yet capable of carrying light at immense speed. This made the ether strange but not useless. Many scientific ideas begin by stretching the imagination. The fact that something is difficult to picture does not make it false. Magnetic fields, electric fields, atoms, and invisible radiation all required people to trust effects before direct sensory familiarity. The ether belonged to a century increasingly comfortable with unseen causes, as long as those causes could organize observation and eventually touch measurement. The 19th century was a world of growing precision. Telegraph wires carried messages across distance. Spectroscopes spread starlight into lines that revealed chemical identity. Electricity and magnetism, once treated as separate phenomena, were drawn into deeper relationship. Instruments were teaching people that invisibility did not mean unknowability. The ether fit that world. To feel how natural this seemed, imagine the 19th century mind standing between two kinds of emptiness. One emptiness was visible at night, the dark space between stars. The other was conceptual, the empty place left in explanation, if light was a wave but had no medium. Ether seemed to fill both at once. It gave the heavens an unseen substance and gave wave theory something to rest upon. The success of wave optics made this need feel stronger. When two beams of light met, they could strengthen or weaken each other in patterns that resembled wave interference. Light could bend around edges in ways that suggested it was not merely a stream of tiny particles flying in straight lines. These observations did not require the ether in exactly the same way for every physicist, but they made the question of a wave medium feel urgent. There had been earlier battles over the nature of light. Newton's authority had long supported a particle-like view, but experiments and mathematical work had given the wave picture new power. By the 19th century, the wave theory of light was not a fringe idea. It was one of the great explanatory successes of physics. Yet its success seemed to demand a carrier. The ether was the answer that kept the victory from becoming incomplete. It also connected light to a larger dream of unity. The 19th century did not only study isolated phenomena, it increasingly looked for deep relationships. Electricity and magnetism were drawn together. Light became linked to electromagnetic waves through Maxwell's theory. Heat, energy, motion, and matter were being reorganized into more powerful frameworks. In such a world, ether seemed less like an optional decoration and more like the hidden fabric that might make the connections possible. This is why the ether could be both scientific and mysterious. It was not visible, but neither were many of the century's most important entities. Its strangeness was not enough to remove it from serious thought. The real problem was that it had to be given properties that were difficult to reconcile. It had to be almost infinitely yielding to planets, yet capable of transmitting vibrations with extraordinary speed. It had to fill the universe, yet not behave like any material found on Earth. The idea, therefore, had a double nature. It made light easier to imagine, but the more one asked what kind of substance it must be, the more difficult it became. That difficulty did not make the ether weak at once. In many sciences, a concept can be fruitful before it is fully understood. The atom, for example, was debated and refined long before it could be treated as familiar physical reality. Fields were invisible, yet they could organize the behavior of forces. A concept could earn its place by explaining patterns, even while its deeper nature remained uncertain. Ether had earned that kind of provisional authority. It allowed physicists to speak about light as a wave in a universe that did not feel empty. It helped preserve mechanical imagination at a time when science still sought underlying mechanisms. It offered a background against which motion might be measured. It gave the universe a hidden stage, a place where light's vibrations could unfold. But the stage was becoming testable. It gave light a medium. It preserved the analogy between light waves and other waves. It made the darkness between stars feel less empty, less like an impossible void, and more like a hidden continuity through which brightness could travel. This is important because it prevents the story from becoming arrogant. It is easy to look backward and treat old theories as simple mistakes. But good history asks why intelligent people found them persuasive. Ether was persuasive because it answered a real problem within the physics of its time. If light was wave-like, the ether made the wave feel physically grounded. Still, the idea carried tensions from the beginning. The ether had to be unlike ordinary substances in almost every way. It could not be thick like water because planets did not plow through it with visible resistance. It could not behave like air because it had to exist in places where air did not. It could not be easily dragged, yet perhaps it interacted with matter in some way. It had to be rigid enough to transmit waves of light, but subtle enough not to disturb celestial motion. The more one thinks about it, the stranger it becomes. But strangeness alone does not end a theory. What matters is whether the theory can meet the world. If ether filled space, and if the earth moved through space, then the earth should move through ether. That movement, if the medium was stationary in some cosmic sense, should create something like an ether wind. The phrase is a metaphor, but a useful one. A person moving through air feels wind, even if the air is still relative to the ground. A boat moving across water must deal with the current. Motion through a medium often has a direction, a resistance, a measurable effect. No one expected the ether wind to touch skin or bend a candle flame. The ether was too subtle for that. But perhaps light itself would be affected. This was the hope. If the earth moved through the ether, then light traveling along the direction of that motion might behave slightly differently from light traveling across it. The difference would be tiny, but not impossible to seek. It would not show itself to ordinary senses, but an optical instrument might reveal it. This is the bridge from idea to experiment. The ether began as a conceptual necessity. It made wavelight seem possible. But once it was imagined as a real medium, it could not remain purely conceptual. It had to have consequences. If those consequences could be predicted, then they could be tested. The invisible ocean had to become experimental. That transformation is one of the quiet strengths of science. A broad idea is not simply admired from a distance. It is narrowed. It is asked to make contact with a specific measurement. It is brought into a room, into an instrument, into a pattern of light and shadow. The question becomes smaller, but also sharper. For ether, the sharpened question was simple in form. Can the Earth's motion through it be detected? The answer was not easy to obtain. The effect would be extremely small. Light moved too quickly for direct comparison by ordinary means. A laboratory on Earth moved with the Earth, so there was no simple outside vantage point. The experiment had to be indirect. It had to compare light with light. It had to turn tiny differences in travel time into something visible. That is why the ether story leads naturally to Michelson. It required a scientist who believed that precision could reveal what the senses could not. It required someone willing to turn a grand, cosmic idea into a delicate optical test. The ether had filled the universe in imagination. Now it had to leave a sign in an apparatus. Before that sign was missing, it seemed reasonable to expect it. This point matters for the emotional weight of the documentary. If the ether had been absurd, Michelson and Morley's null result would not carry much tension. But if ether had once seemed almost necessary, then the failure to detect its wind becomes a deeper wound. It does not merely remove a fantasy. It unsettles a structure of explanation. At the same time, the ether was never a single, simple object. Different physicists imagined different ways it might behave. Some thought matter might drag it partly. Some explored whether the ether near Earth could share Earth's motion. Others tried to preserve a stationary background. This variety would later matter because a failed detection did not automatically eliminate every possible ether theory. The story must stay careful here. The need for care is especially important because the ether was not a single fixed object in every theory. Some versions treated it as almost perfectly stationary, a universal rest frame. Others imagined that matter might drag it partially along. Still others adjusted its behavior to account for optical observations that did not fit simple expectations. The ether was a family of ideas, not one simple substance, waiting to be knocked down by one blow. This is why Michelson and Morley's experiment did not end every debate immediately. It challenged a particular expected effect, the measurable motion of the Earth relative to the luminiferous ether. It made one path difficult. It did not erase every possible way a physicist might try to preserve a medium of light. But that does not make the experiment weaker. In fact, it makes the history richer. A crude story says everyone believed in ether, one experiment disproved it, and then Einstein replaced it. The more accurate story is quieter. Ether was useful. Ether was strange. Ether became experimentally vulnerable. Michelson and Morley failed to detect the expected wind. Then physics entered a long period of interpretation repair and conceptual pressure. That slow pressure is where the true drama lives. A great idea is rarely defeated by being mocked. It is defeated or transformed by being taken seriously enough to test. The ether had once helped make sense of light. Now it had to survive the demand that it leave a measurable trace. Michelson and Morley did not destroy all imaginable ethers in one experiment. They challenged a particular expectation tied to the idea of relative motion between the Earth and a luminiferous ether. Their result made the older picture harder to sustain, but physics would spend years trying to interpret what had happened. In this section, however, the ether is still alive. It stretches through the scientific imagination like a hidden sea. It carries light across darkness. It reassures the mind that waves have a medium. It belongs to a universe where invisible causes can be made respectable by mathematics and measurement. And the Earth is sailing through it. That image creates the tension. If the Earth is sailing, then where is the current? If the hidden ocean fills space, why does it not leave a trace? If light depends on that medium, can light itself reveal the medium's presence? The 19th century had learned to trust instruments in pursuit of such questions. A spectroscope could make a star speak chemically. A galvanometer could show an electric current. A microscope could reveal structures hidden from the naked eye. A carefully designed optical instrument might now reveal the medium of light itself. The task required more than belief. It required a device that could ask the question in the language light understood. This is where the story turns toward the human maker of the instrument. The ether gave the problem its cosmic scale, but the experiment would depend on a person willing to work at the scale of fractions, fringes, and almost invisible differences. The invisible ocean needed a listener. Albert Michelson would become one of the most precise listeners light had ever found. Albert Michelson enters this story not as a man trying to overturn the universe, but as a man trying to measure it more carefully. That distinction matters. Later history would place his name beside one of the most famous null results in physics. But Michelson did not begin with the role of a revolutionary. He belonged to the discipline of exact measurement, to the patient world of optical instruments, timing alignment, and comparison. For him, light was not only illumination, it was a tool. Light could be reflected, divided, delayed, recombined, and read. It could become a ruler, finer than ordinary rulers. It could expose differences too small for direct touch. In a century fascinated by measurement, Michelson found his work in the place where precision became a way of asking nature to speak more clearly. He had a background shaped partly by naval education and practical science. That world valued accuracy in timing, navigation distance, and observation. Such concerns are not romantic at first glance, but they form a powerful habit of mind. To know where one is, to measure a path, to compare signals, to trust an instrument, all of these practices train attention towards small errors and exact corrections. Michelson brought that attention into physics. The culture of precision that shaped Michelson was not merely personal. It belonged to a wider transformation in science. The 19th century had become an age of improved instruments, better clocks, better lenses, better standards of length, better electrical devices, better methods for comparing small quantities. Knowledge was no longer built only by grand theories and visible demonstrations. It was built by reducing error. Error became an enemy with many forms. It could hide in the uneven surface of a mirror, in the warmth of a room, in the expansion of metal, in the vibration of a floor, in the limits of the human eye. It could enter through impatience or through a theory that made the observer see what they expected. To work precisely was to develop suspicion toward one's own conditions. It was to know that nature could only be heard clearly after the instrument and the observer had been disciplined. Michelson's world was full of this discipline. The speed of light in particular invited an almost heroic form of measurement. It was too fast for common experience and too fundamental to ignore. Earlier experimenters had found ways to estimate it, but Michelson pushed toward refinement. His work belonged to a tradition in which the value of a number was not just a number. It was a measure of how far human technique had advanced into the invisible. To measure light more accurately was to bring one of nature's most elusive constants closer to human order. This helps explain why the ether experiment was a natural extension of his work. If light could be used to measure itself, if interference could reveal tiny differences, then perhaps the same optical discipline could detect the Earth's hidden motion through the medium of light. Michelson did not have to be a philosophical rebel to attempt this. He only had to believe that a precise enough instrument could make a subtle effect visible. One of his lasting concerns was the speed of light. Today, many people know the speed of light as a fixed number printed in textbooks and treated almost like a fact beyond history. But in Michelson's world, measuring it with greater accuracy was a serious challenge. Light was so fast that its movement across earthly distances seemed almost instantaneous. To measure it, scientists had to design clever methods that turned tiny intervals into readable effects. Michelson was drawn to that kind of challenge. He was not discouraged by smallness, a slight delay, a delicate shift, a narrow optical fringe. These were not trivial details to him. They were places where nature could be made exact. His imagination was not theatrical. It was instrumental. He seemed to trust the idea that if one could reduce uncertainty enough, even an invisible effect might become accountable. The interferometer was the perfect expression of that trust. In principle, its operation was simple. A beam of light could be split into two paths and then brought back together. If the two beams returned out of step with one another, the resulting pattern of light and darkness would reveal the difference. The instrument did not need to watch light travel in slow motion. It used light's own wave behavior to compare one journey with another. But the simplicity of the idea hid the difficulty of the practice. The mirrors had to be aligned. The light paths had to remain stable. The observer had to distinguish real movement from disturbance. Heat vibration, mechanical imperfection, and human limitation all stood between the question and the answer. A device built to notice very small differences is also vulnerable to very small errors. Precision is never just sharpness. It is discipline. Michelson understood this. His work with optical methods gave him the kind of patience the ether problem required. If the Earth's motion through ether produced only a tiny effect on light, then ordinary observation would never reveal it. The effect would have to be magnified through design and protected from noise. This is where his scientific temperament becomes central. The search for ether wind was not a search for something visible. It was a search for a difference between two optical paths. Only a person deeply committed to the meaning of small differences could turn that search into a serious experiment. Michelson's strength lay in taking what others might treat as too slight and making it measurable. Still, the famous Cleveland experiment was not Michelson's work alone. Edward Morley deserves his place in the story. He was not merely an assistant attached to a famous name. Morley was a careful experimental scientist with his own reputation for exact work. His collaboration helped make the later version of the experiment more stable and more difficult to dismiss. Morley's importance also gives the story a second kind of precision. Michelson's name is often remembered first because the interferometer became so closely associated with him, but Morley brought his own habits of exact experimental work. He was a chemist, and chemistry in that period demanded careful attention to weights, substances, purity, and repeatability. His scientific temperament complemented Michelson's optical focus. This mattered because the 1887 experiment was not merely a matter of clever design. It was a matter of making the design physically trustworthy. The earlier attempt had shown how difficult the problem was. A more stable setup was needed. The apparatus had to be better protected from vibration. The turning mechanism had to be smoother. The whole arrangement had to make it harder for critics to say that the missing effect was only the result of poor conditions. Morley's contribution helped give the experiment that authority. The collaboration also reminds us that science is often less solitary than its later legends suggest. A famous result may carry one or two names, but behind it stand materials, workshops, buildings, institutional settings, previous attempts, and conversations between people with different skills. The Michelson-Morley experiment belongs to the history of ideas, but also to the history of craft. It was not only thought, it was construction. A mirror had to be placed, a beam had to be guided, a stone had to be supported, a liquid metal had to hold weight and permit motion. The question had to become hardware before it could become evidence. This physicality matters for the listener. The experiment can sound abstract when described as a test of relative motion through the ether. But inside the laboratory, the question was handled through objects. The invisible was approached by arranging the visible with extraordinary care. That is where the beauty of experimental science often lies. If Michelson brought the optical method, Morley helped strengthen the physical conditions under which the method could work. The problem was not simply how to split a beam of light. The problem was how to give that beam a trustworthy world to move through. The apparatus had to rotate. It had to remain steady while rotating. It had to keep its mirrors aligned and its optical paths stable. It had to be sensitive enough to show the expected effect, but not so fragile that every tremor became false evidence. This is why the material construction of the experiment matters. The stone slab, the mercury bath, the slow-turning apparatus, these details are not decorative. They reveal the seriousness of the attempt. Michelson and Morley were not making a vague philosophical gesture. They were narrowing an old idea into a physical test and then building the conditions under which that test could be trusted. To detect something almost weightless, they needed weight. To find motion through an invisible medium, they needed steadiness. To compare beams of light, they needed stone mirrors, glass, and a liquid metal dense enough to carry a heavy platform smoothly. The experiment was both cosmic and earthy. This contrast gives it much of its beauty. In imagination, the ether stretched across the universe. In practice, the search for it depended on the behavior of screws, surfaces, supports, reflections, and the patience of observers. A vast invisible idea had to pass through the discipline of a basement apparatus. Michelson's obsession with precision made that passage possible. He was not mainly a theorist building a new picture of space and time. His genius lay in measurement and in the construction of instruments that could make measurement finer. Later, he would be recognized for optical precision and metrology, for the way his instruments and methods expanded what physics could examine. But in the ether experiment, that broader gift was focused on a single haunting question. Could the motion of the Earth through the medium of light be detected? The question was extraordinary because of the difference in scale. The Earth was immense. Its motion through space was astronomical. The expected effect inside the apparatus was tiny. A whole planet's movement had to become a slight change in the relation between two beams of light. That is what precision does. It connects scales that ordinary perception cannot connect. A person standing in the basement could not feel the Earth's orbit. The stone slab did not visibly race through space. The light moved too quickly to be followed. The ether could not be seen. Yet the experiment claimed that under the right conditions, the motion of the planet might become legible as a shift in optical fringes. For a moment, a basement became an observatory of motion, not an observatory aimed outward like a telescope. This one looked inward into the relationship between light and itself. It did not enlarge the moon or reveal the rings of Saturn. It compared two paths and asked whether one carried a trace of the Earth's direction through a hidden medium. A casual observer might have seen only lines of brightness and darkness. Michelson saw the possibility of a cosmic measurement. This is where the human story becomes quietly intense. Scientific patience is often less visible than scientific imagination, but it can be just as powerful. To return to the apparatus, to adjust, to observe, to repeat, to control errors, to care about a fringe shift that most people would never notice, all of this requires a certain temperament. Michelson and Morley's seriousness gave the result its later force. If the experiment had been sloppy, the missing effect could have been dismissed. If the apparatus had been crude, the null result would have meant little. If the question had been poorly formed, the ether might have escaped untroubled. But the experiment was careful enough that its failure to find the expected effect became uncomfortable. This is one of the most important truths in the documentary. Precision does not merely confirm theories. It can endanger them. It strips away vagueness. It forces a broad idea to meet a narrow test. It says, in effect, if this is true, then here is one place where it should show itself. The ether had lived as a grand explanatory medium. Michelson and Morley brought one consequence of it into the room and asked it to appear in the fringes. That was a dangerous kindness. It was kind because it gave the idea a chance to become measurable. It was dangerous because measurement can reveal not only presence, but failure. The more carefully nature is asked, the less easily a theory can hide behind metaphor. Michelson's work therefore prepared the central drama. He did not destroy ether by argument. He did not replace the old worldview by speculation. He helped build an instrument that made the old worldview answer a specific question. That is why his precision matters more than any dramatic personality portrait. He made light into a judge of motion. The phrase is simple, but its meaning is deep. Light, which filled ordinary life softly and invisibly, became a tool for testing the hidden structure of space. A beam that might have merely illuminated a room was divided, compared, and made to carry the weight of a scientific assumption. Morley's role made that judgment steadier. The apparatus became more stable, the conditions more controlled, the experiment more serious. Together, Michelson and Morley gave the question its best chance to become visible. And that is what made the result so troubling. The old idea was not brushed aside by impatience. It was treated with care. It was given a delicate machine, a controlled environment, a repeated test, and observers trained to read small optical signs. The ether was not ignored. It was listened for with extraordinary attention. The expected signal still did not appear. Before reaching that moment fully, however, we need to follow the machine itself more closely. We need to understand how a beam of light could be divided into two journeys, why the two journeys were expected to differ, and how rotating the apparatus turned a local optical pattern into a test of planetary motion. The obsession with precision had prepared the question. Now the machine had to ask it. The question was ready to become mechanical. It was no longer enough to say that light might need a medium or that the Earth might be moving through that medium. If the ether was real in the way many physicists imagined, then its presence had to produce some measurable consequence. The challenge was to create a machine delicate enough to expose it. Michelson and Morley's apparatus was built for that purpose. At first, the idea can seem difficult because the experiment did not capture anything. It did not collect ether in a vessel. It did not weigh a substance. It did not make the invisible ocean visible. Instead, it compared two journeys of light and looked for a change in the relationship between them. The heart of the instrument was the interferometer. To follow the instrument, it helps to slow the beam down in imagination, even though in reality light moved far too quickly for the eye to follow. First, the beam reached the central optical element where it was divided. One portion continued along one arm of the apparatus. Another portion turned sideways. From that moment, the two beams became like two messengers sent from the same origin by different roads. Each carried the same beginning, but each was asked to travel through a different relation to the supposed ether wind. At the end of each road stood a mirror. The mirrors did not merely send the beams back. They completed the comparison. Each returning beam carried the history of its journey, the distance it had traveled, and the time it had taken. When the beams met again, they overlapped. Their waves either reinforced or weakened one another, creating the pattern of fringes that the observers could inspect. This is why interference was so powerful. It made the beams compare themselves. It did not require the experimenters to hold a clock fine enough to time light directly across the apparatus. The light waves became the clock, or at least the record of a difference that no ordinary clock could reveal. The pattern was delicate because light is wave-like. A crest meeting a crest strengthens brightness. A crest meeting a trough weakens it. Across the field of view, this relationship forms bands. Move one path slightly relative to the other, and the bands move. The eye does not see time, but it can see the consequence of a time difference translated into light and dark. That translation was the heart of the machine. It is worth lingering here because it turns the experiment from a strange historical event into something almost intuitive. Michelson and Morley were not asking the ether to show itself as substance. They were asking whether two light beams sent in different directions through the moving world would return with a difference in their step. If they did, the fringes would tell. A beam of light entered the apparatus and struck a partially silvered mirror or a piece of glass that allowed some of the beam to pass through while reflecting the rest sideways. In that moment, one beam became two. One path continued forward, the other turned at a right angle. Each beam traveled along an arm of the instrument. Each reached a mirror. Each reflected back toward the center. When they met again, they did not simply become ordinary light. They formed an interference pattern with bands of brightness and darkness created by the way the light waves overlapped. This pattern made tiny differences visible. If one beam traveled a slightly longer optical path, or took a slightly different time, the waves would return out of step. The bright and dark bands would shift. The observer would not be measuring light's travel time directly with a clock. Instead, the observer would read time difference as a change in pattern. This was the instrument's brilliance. It translated a hidden difference into something the eye, aided by the apparatus, could inspect. A timing difference too small for an ordinary clock could become a displacement of fringes. A subtle effect of motion, if present, could become an optical sign. The ether wind was expected to create just such a difference. Imagine, gently, a boat in moving water. A boat traveling with or against the current does not behave exactly like a boat crossing the current sideways. Its timing and path reveal the medium through which it moves. The ether was not water, and the analogy should not be pushed too far, but the intuition was similar. If the earth moved through ether, then light, traveling in different directions relative to that motion, might take slightly different times to complete the same kind of journey. One beam would travel along one arm, another would travel along the perpendicular arm. If one arm happened to lie more nearly along the direction of the Earth's motion through ether, then its beam should be affected differently from the beam traveling across that motion. When the beams returned and reunited, the interference fringes should reveal the difference. But the apparatus did not remain fixed in one orientation. It rotated. That rotation was crucial. By turning the whole instrument, Michelson and Morley could change the relation between the two arms and the supposed ether wind. The arm once aligned more nearly with the motion would become transverse. The arm once transverse would become more aligned. If the ether wind existed in the expected way, the pattern should drift as the apparatus turned. The machine was therefore asking the same question from multiple directions. This is a beautiful experimental gesture. The Earth itself could not be stopped or turned for comparison. No scientist could step outside the planet and hold the laboratory still. But the apparatus could be rotated on the Earth. The instrument could change its orientation within the larger motion and see whether light responded. A small machine became a way of testing a planetary journey. This is one reason the experiment has such lasting power. The room looked still, but physics insisted it was not. The building rested on the Earth, and the Earth was moving. The apparatus stood in the basement, but the basement was being carried around the sun. If a stationary ether filled space, then the stillness of the room was only apparent. The interferometer was built to expose that false stillness. The expected effect depended on the idea that one path of light would be in a sense more affected by motion through the ether than the other. If the apparatus moved through a stationary medium, then the beam traveling along the direction of motion would face a different timing problem from the beam traveling across the supposed wind. The details are mathematical, but the feeling is simple direction should matter. That is why rotation was essential. A fixed apparatus might leave too much ambiguity, but a rotating apparatus could change the relation of its arms to the supposed wind. If the effect was real, it should vary as the instrument turned. The movement of the fringes would not be just any movement. It would have a pattern tied to orientation. In this sense, the experiment had a rhythm. Set the apparatus, observe, turn, observe again, continue, compare. The answer would not come from one dramatic instant, but from consistency across positions. The experiment asked whether nature would repeat the expected sign as the machine moved through its orientations. There is something very patient in this method. A person could not hurry the result into existence. The observer could only create the conditions, turn the instrument, and watch. This is the opposite of forcing a theory onto nature. It is a disciplined form of waiting. The waiting mattered because the experiment stood between two worlds of motion. One was the motion felt inside the room, almost none. The other was the motion known from astronomy, immense and constant. The interferometer tried to connect these two scales. It tried to turn planetary motion into optical displacement. That connection is what made the missing shift so powerful when it came. It had to do so under difficult conditions. The expected shift was very small. A vibration could imitate movement. A slight change in the apparatus could blur the result. Heat could expand or contract parts of the machine. A floor that seemed solid in ordinary life could be too restless for optical precision. So the apparatus needed protection from the world it occupied. The heavy sandstone slab provided stability. The mercury bath allowed smooth rotation. The mirrors and optical paths were arranged so that the whole system could turn without disturbing the delicate comparison. The design was not simply clever. It was a response to the fragility of the question. A stone floated on metal so that light could test the motion of the earth. The image is worth holding. Stone, mercury, glass, light. Heavy matter and swift radiation. A basement and a cosmic medium. Human hands arranging ordinary materials so that an invisible assumption might show itself as a small shift in brightness and darkness. The experiment had a quiet confidence, but also a discipline of limitation. It did not ask everything about ether. It did not solve every question about light. It asked whether the Earth's motion relative to a luminiferous ether could be detected by comparing two perpendicular light paths. That narrowness made it powerful. A grand theory had to risk one concrete prediction. Good experiments often work this way. They do not conquer the whole unknown at once. They create a place where one consequence must appear or fail to appear. They take a large idea and bring it to a small gate. If the idea passes, confidence grows. If it does not, the difficulty begins. Michelson and Morley had built such a gate. The expected result was a fringe shift, not a dramatic motion visible across the room, but a slight displacement in the interference pattern as the instrument rotated. A trained observer could read it. The size of the predicted shift came from the logic of motion through ether and the geometry of the apparatus. If it appeared, the old picture would gain support. The ether wind would have become measurable. The invisible ocean of light would not be directly seen, but it would leave a trace. The Earth's motion through it would be written into the behavior of light in a basement. That would have been a powerful confirmation of a medium many scientists already found plausible. But the experiment also carried a second possibility. If the shift did not appear, then something would be wrong. Perhaps the apparatus was not sensitive enough. Perhaps the ether behaved in an unexpected way. Perhaps matter and motion altered the instrument itself. Perhaps the whole idea of a detectable ether wind was misguided. The machine did not decide in advance which future science would enter. It only arranged the test. This is why the apparatus should not be described only as a technical device. It was a fork in the road. Before the result, both routes remained open. The ether might show itself, or the experiment might return a failure that was too careful to ignore. The drama lay in the smallness of the sign. For a broad audience, it is natural to expect experiments to produce obvious transformations. A liquid changes color, a spark leaps, a needle moves, a screen lights up. The Michelson-Morley experiment asked listeners to care about something subtler, whether a pattern of fringes shifted slightly as the apparatus turned. Yet the history of science often depends on such slight things. A line in a spectrum can reveal an element. A small deviation in a planet's orbit can suggest a deeper theory of gravity. A tiny residue can change chemistry. A missing fringe shift can unsettle an entire way of imagining light. In Cleveland, the scale of the sign was small. The scale of the meaning was not. The observers had to return to the pattern again and again. One reading could be misleading. One orientation could be affected by local disturbance. The experiment required repeated care. The point was not to create a single dramatic instant, but to test whether the predicted shift consistently emerged as the apparatus rotated. Repetition also protected the experiment from wishful thinking. When a result is expected, especially a subtle one, the mind can become eager. A small tremor may look meaningful. A slight drift may be tempting to interpret. Careful science must resist that temptation. It must ask whether the effect appears in the right way at the right time with the right relation to the changing orientation of the apparatus. Michelson and Morley were therefore not simply watching light. They were watching for a disciplined pattern within light. The question was not whether the fringes ever moved at all. Optical setups are never perfectly frozen. The question was whether the movement matched the predicted signature of ether drift. This is an important distinction. A casual listener might think the experiment depended on seeing no movement whatsoever. But the deeper issue was expected movement of the right size and form. Real experiments contain noise, uncertainty, and small variations. The challenge is to separate these from the theoretical signal. The famous result comes from the failure to find the predicted signal, not from some mystical perfection of stillness. This keeps the story scientifically grounded. The beauty of the experiment lies not in the fantasy that the room was perfectly silent, but in the fact that the expected effect did not emerge from careful observation. The apparatus had been built to detect a particular consequence of ether theory. That consequence failed to appear as required, in the quiet language of measurement that was enough to disturb a universe. The machine asked patiently. The light divided, traveled, reflected, and reunited. The stone turned. The mercury supported the motion. The fringes were watched. The same question was posed from one orientation to another, like a quiet interrogation of space itself. If the ether wind was there, the fringes should betray it. This is where the apparatus becomes more than an instrument of optics. It becomes a meeting point between human expectation and physical reality. Theory had said that a certain effect should be found. Engineering had created a way to look. Observation would now decide whether the expected trace appeared. The question had been made as precise as it could be. That precision gave the coming result its weight. The experiment would not be remembered because it was the largest apparatus of its age or the loudest demonstration. It would be remembered because it narrowed a cosmic idea into a measurable optical event and then failed to find the event in the expected form. The machine was built to catch the Earth moving, not by watching the planet from outside, but by comparing light from within. Not by seeing ether, but by asking whether light's two journeys carried the sign of motion through it. Not by trusting intuition, but by letting an interference pattern become the judge. So the apparatus turned. The light returned to itself. The fringes waited to reveal the hidden current. The Earth moved through space with the room upon it, and the experiment approached the result that would make it famous. The machine had been built for a movement so small that no one in the room could feel it. If the Earth was passing through the ether, then the turning apparatus should have revealed a faint displacement in the interference fringes. The effect would not be theatrical. It would not announce itself as a flash or a sound. It would be a subtle drift in a pattern of light, meaningful only because the experiment had been designed to notice it. The beams traveled their paths. They reflected from their mirrors. They returned and met again. The apparatus changed orientation. The observers watched the fringes. The expected shift was not found. This is the strange center of the story. Nothing broke. Nothing exploded. The room did not suddenly reveal the hidden medium. Instead, the predicted effect remained absent or far smaller than the theory had led them to expect. The apparatus listened for the ether wind and did not hear it in the expected way. To understand why this mattered, We must keep the prediction in view. The experiment was not a vague search for mystery. It had a clear purpose. If the Earth moved through a stationary ether light traveling in one direction, should complete its journey slightly differently from light traveling at right angles. As the apparatus rotated, that difference should change, and the interference pattern should move. The test asked for a measurable sign, not a large sign, not one that ordinary senses could catch, but a sign consistent with the expected motion through ether. The problem was that the observed result did not match that expectation. The shift was not there in the needed form. At first, this can feel unsatisfying as a story. A discovery often gives the imagination something to hold a new planet, a new ray, a fossil, a chemical element, a track in a detector. Michelson and Morley gave science something more difficult. They gave it a failed expectation under careful conditions. That is not the same as nothing. An absence becomes meaningful only when something should have appeared. The absence of a sound matters if one was listening for a bell. The absence of a star matters if a calculation said it should be visible. The absence of a fringe shift mattered because the ether theory in that experimental form led physicists to expect one. So the event was not that nothing happened. The event was that the expected thing did not happen. This distinction is essential. A careless question can receive no answer and teach little, but a precise question asked by a sensitive instrument can turn a missing result into evidence. The missing fringe shift did not immediately solve the problem of light. It did not instantly prove that every possible ether idea was false, but it damaged a specific and important expectation. The Earth's motion through the luminiferous ether had not been detected as anticipated. The result also had an unusual emotional shape. Many scientific disappointments are private and disappear quickly. An apparatus fails. A reading is inconclusive. A sample is contaminated. A hypothesis proves unproductive. The work is set aside, and history barely notices. This was different because the experiment was attached to a central picture of nature. The ether was not a minor detail. It was part of how many physicists imagined light itself. To fail to detect ether drift was not like failing to find a rare mineral in one valley. It was like failing to find the expected footprint of a concept that had seemed to fill the universe. The missing shift, therefore, had a scale larger than the apparatus. Inside the room, the effect was tiny. In theory, the effect touched the structure of light and space. The experiment compressed a cosmic assumption into an optical detail, and when that detail failed to appear, the whole assumption became less secure. That compression is what makes the result memorable. The scale of the question and the scale of the sign were wildly different. A universe filled with ether, a planet moving through it, a beam of light divided into two paths, a fringe pattern expected to shift. The entire chain led from the heavens to a delicate optical band. Then the chain broke at the last link. For the scientists of the time, the meaning was not simple. The ether had been too useful, too deeply woven into wave theory to be discarded overnight. It had helped make light intelligible. It provided a medium for the waves that interference and diffraction seemed to require. A single experiment, even a careful one, did not erase the need many physicists felt for some underlying carrier of light. But the result remained. It became a small, stubborn fact. It could be questioned, reinterpreted, explained away for a time, or folded into new theory. But it could not simply be made to vanish. A sensitive test had looked for a predicted effect. The effect had not appeared. This is the beginning of scientific pressure. Not the pressure of public drama, but the pressure of a fact that does not fit comfortably. A theory can survive such pressure. Many theories do. But survival is not the same as peace. The theory must now carry the difficulty wherever it goes. If the ether existed, why was its wind not detected? Was the ether dragged along by the earth? Did the apparatus change as it moved? Was the prediction incomplete? Was the medium unlike the medium people imagined? Or was the whole search for motion relative to a stationary ether based on the wrong kind of question? The experiment did not answer all of these at once. It made them necessary. That is why the Michelson-Morley result became powerful in retrospect. It did not close the story with a simple statement. It opened a field of unease. It turned the ether from a reassuring background into an object of defense. It made physicists work harder to keep something that had once seemed natural. There is a quiet psychological shift here. Before the experiment, ether could be imagined as the hidden ocean that made light waves possible. After the experiment, that ocean had to explain why a machine built to detect its current did not find the expected trace. The burden had changed. The ether was no longer only an answer to the wave question. It had become a problem in measurement. The old picture had not collapsed, but it was less comfortable. This matters because science is not only a collection of facts, it is also a relationship between facts and expectations. When the two fit, a theory feels strong. When they do not, a theory may still survive, but its authority becomes conditional. It must become more precise, more qualified, or more complicated. Michelson and Morley's result demanded that kind of response. It also humbled the culture of precision in a particular way. The 19th century had learned that instruments could reveal hidden worlds. Spectroscopes had read the chemistry of stars. Electrical instruments had traced unseen currents. Microscopes had exposed living structures too small for the naked eye. Precision often revealed what had been invisible. Here, precision revealed that something expected did not show itself. That is a different gift. It is easier to celebrate an instrument that finds. It is harder to honor one that fails to find, especially when the missing thing is attached to a cherished theory. But the discipline of science depends on respecting both kinds of result. A careful instrument has the right to disappoint the mind. The basement in Cleveland became such a place of disappointment, but disappointment is not the same as defeat. It can be the beginning of refinement. A result that disappoints a theory may be treated as an error at first, but if it keeps returning, and if related attempts also fail, the disappointment changes character. It becomes a demand for explanation. That demand was the true legacy of the null result. It asked physicists to make a choice, though, not immediately and not all at once. They could question the apparatus. They could modify the ether. They could change their assumptions about matter. They could eventually change their understanding of space and time. The experiment itself did not choose among all these. It simply made the old expectation unstable. There is a kind of restraint in this. The experiment did not overstate itself. It did not declare a complete metaphysical truth. It gave a result within a defined setup. But because that setup touched a major theoretical expectation, the result had consequences beyond its narrow form. This is one of the ways science turns modest statements into deep transformations. A careful local result can slowly become a global pressure. That is why the missing shift should not be treated as emptiness. It was more like a weight placed gently on a structure that already had hidden cracks. At first, the structure still stood, but the pressure revealed where support was needed, where assumptions had been too easy, and where old explanations no longer rested as comfortably as before. The story now had to move from experiment to defense. The ether would not vanish, it would adapt. The disappointment was not empty. It had shape. The light paths were known. The apparatus had a purpose. The predicted fringe shift had a theoretical reason behind it. The result, therefore, pressed against a specific part of the old view. It said not that science was broken, but that one expected consequence had failed. The word null result can sound cold, but in this case it carries weight. A null result does not mean nothing was learned. It means the experiment did not find the effect it was designed to test. Whether that matters depends on the quality of the test and the strength of the prediction. Here, both were significant enough to make the result memorable. The experiment failed as a search for the ether wind. It succeeded as a test of the expectation that such a wind should be detectable in that way. That paradox is the heart of the documentary. The experiment did not give Michelson and Morley what they sought. It gave physics something else, a difficulty that could not be easily set aside. The absence of the predicted shift became a presence in scientific thought. Still, the history must remain careful. It would be too simple to say that the ether died in that basement. The immediate response was more gradual. Scientists considered ways to rescue the ether. They explored whether the Earth dragged the ether along, whether matter behaved differently in motion, whether the apparatus itself changed. The old idea was not abandoned without resistance. That resistance is part of the story. A serious theory deserves serious rescue attempts. If a framework explains much, scientists do not discard it at the first sign of trouble. They test the trouble. They refine assumptions. They ask whether the experiment has been interpreted correctly. They search for a way to preserve what still works. The ether had earned that effort. But every rescue attempt also revealed how difficult the situation had become. The experiment had not produced a simple replacement, but it had created a gap between prediction and observation. The gap had to be filled somehow. The more carefully one filled it, the more the old picture changed. A theory under strain can survive for a long time, but it no longer breathes the same way. Return once more to the room. The apparatus turns. The light divides and returns. The fringes are examined. The Earth is moving, but the expected sign of its movement through ether is not there. The pattern does not become the announcement the old theory hoped for. That stillness did not prove the Earth was motionless. It did not remove mystery from light. It did not immediately create a new physics. It did something subtler. It showed that the old way of linking light, ether, and motion had failed one of its most elegant tests. For a scientist, such a result is dangerous because it does not let the mind rest. It does not say, here is the new answer. It says, your old answer is incomplete. It does not close the book. It places a mark in the margin that future readers cannot ignore. The result became a room between worlds. On one side stood a physics that wanted light waves to travel through a medium. On the other side waited a physics that would no longer need the old luminiferous ether in the same way. Between them was the experiment, not yet a full bridge, but a narrow plank laid across uncertainty. The expected effect had refused to appear. Now physics had to decide what kind of refusal it was. The experiment left physics with a problem, but not with an immediate replacement. That is why the next part of the story is not a clean farewell to the ether. It is a rescue attempt. The old idea did not vanish simply because Michelson and Morley had failed to find the expected ether wind. Ether still had intellectual work to do. It still seemed to answer the question of what carried light waves. It still belonged to a successful tradition of wave optics and electromagnetic theory. So physicists tried to save it. This was not foolish. It was normal science under pressure. When a powerful idea meets a difficult result, scientists do not always throw the idea away. They examine the experiment. They question hidden assumptions. They ask whether the theory can be refined. They try to preserve the parts that still seem necessary while explaining the parts that no longer fit. The ether was too important to abandon without a struggle. One possibility was that the Earth somehow dragged the ether along with it. If the medium near the planet moved together with the Earth, then an experiment on Earth might fail to detect a wind. The laboratory would not be rushing through a still ether. It would be surrounded by ether carried along at least partly by the planet. This idea had its appeal but also its difficulties. If the Earth dragged ether fully, then other optical phenomena, especially observations involving starlight, became hard to explain. The behavior of light from distant stars had already placed limits on simple drag theories. A complete dragging of ether by the Earth did not easily fit the broader evidence. The ether could not simply be carried along like air inside a closed carriage. It had to behave more subtly. That subtlety became the challenge. The ether had to be present enough to carry light, but elusive enough not to reveal Earth's motion through it. It had to remain central to theory while slipping away from the most direct attempt to catch its wind. The old invisible ocean was becoming difficult to hold. Part of the difficulty came from the fact that the ether was expected to do several jobs at once. It was supposed to carry light waves. It was supposed to provide a kind of absolute rest frame. It was supposed to remain compatible with astronomical observation. It was supposed to interact with matter enough to make light possible, but not so much that it disrupted the motions of planets. Each job created pressure on the others. If ether was completely stationary, then Earth's motion through it should be detectable. If ether was dragged along by Earth, then other observations became difficult. If ether interacted with matter, one had to explain how. If it did not interact with matter, one had to explain how it carried light, and why motion through it left so little trace. The concept that once seemed to complete wave theory had become a balancing act. This is not unusual in science. A theory often begins as a clarifying idea, then becomes more complicated as it is asked to explain more phenomena. The complication does not automatically make it false. Sometimes it shows that the theory is rich, but sometimes it signals that the theory is carrying too much hidden strain. Ether was entering that strain condition. Then came one of the most famous attempts to explain the Michelson-Morley result while preserving the ether, the idea associated with George Fitzgerald and Hendrik Lorentz. Perhaps the apparatus itself changed as it moved through ether. Perhaps objects moving through the ether contracted slightly in the direction of motion. The suggestion is strange, but it was not random. The contraction idea can be heard more clearly if we return to the interferometer. The expected shift depended on the comparison between the two arms of the apparatus. If one arm lay along the direction of motion through the ether, light traveling that way should have a different timing relation than light traveling across the supposed wind. But if the arm itself became slightly shorter in the direction of motion, the timing difference could be reduced or canceled. The instrument would then hide the very effect it was built to reveal. This is a remarkable idea. It means the failure to detect ether drift might not mean there was no ether drift. It might mean that motion through ether changed the measuring device in such a way that the drift could not be seen. The ruler used to measure the effect would itself be altered by the motion that produced the effect. The logic was subtle enough to keep the ether alive. It also made measurement less innocent. Before this, one could imagine the apparatus as a stable judge. It would sit in the moving world and reveal the ether wind. But the contraction hypothesis made the judge part of the case. The apparatus could no longer be treated as a neutral object whose dimensions were simply given. Its length might depend on its motion through the very medium being tested. That is why the idea points beyond itself. Even as it preserved the ether, it weakened the older confidence that length, time, and measurement could remain untouched by motion. The old view was beginning to save itself by borrowing pieces from the future. If the arm of the interferometer aligned with the ether wind became slightly shorter, the expected difference in light travel time could be canceled. The beam traveling along that direction would have less distance to cover. The fringe shift that should have appeared might vanish because the measuring apparatus itself had changed in just the right way. In that picture, the ether was still there. The Earth was still moving through it. Light still traveled in relation to it. But the material instrument contracted as it moved, hiding the effect that Michelson and Morley had expected to detect. At first, this may sound like a desperate patch, but historically, it was more serious than that. Lorentz's work belonged to a sophisticated attempt to understand matter electrons, electromagnetic forces, and motion. He was not merely inventing an excuse. He was trying to connect the behavior of moving bodies with the electromagnetic theory that had already reshaped physics. Even so, the cost was real. The ether survived, but the surrounding world became stranger. A measuring rod could no longer be assumed to keep the same length under all motion. The instrument could not be treated as an untouched observer of ether. It became part of the phenomenon. Its own dimensions might depend on motion through the hidden medium. The search for ether had begun with the hope of finding a current. It now led to questions about the behavior of matter itself. This is one of the most important turns in the story. The experiment did not merely challenge ether. It drew rulers' instruments and measurement into the problem. To explain why the expected fringe shift was absent, physicists had to consider whether the apparatus changed in motion, whether lengths contracted, and whether the familiar background assumptions of measurement were as secure as they seemed. A machine built to test the ether began to test the meaning of measurement. Lorentz's framework allowed the ether to remain as a preferred rest frame, even if motion relative to it could not be detected in the expected way. There might still be a true state of rest somewhere beneath appearances. But if experiments could not reveal motion relative to that state, its role became increasingly peculiar. What does it mean to have an absolute rest frame that cannot be found by experiment? This question was not merely philosophical. It went to the heart of physics. If the ether existed, but every attempt to detect motion through it was neutralized by changes in matter and measurement, then ether was becoming less like a physical medium and more like a hidden scaffolding behind equations. It had not disappeared, but it had withdrawn. The rescue worked in one sense. It made room for the Michelson-Morley result without immediately abandoning ether. But in another sense, the rescue changed the feeling of the old theory. The ether had once made light seem more familiar, more mechanical, more like other waves. Now, preserving it required a world in which moving objects contracted by just the amount needed to hide motion through the medium. The explanation had become more subtle than the comfort it originally provided. This is how scientific tension often builds. One adjustment may be reasonable, a second may be necessary, a third may be elegant. But over time, the older framework can begin to feel burdened. It remains standing, yet it requires more supports than before. The supports themselves become part of the story. Lorentz's work is especially important because it shows how close the old and new worlds could come while still being conceptually different. He developed transformations that related measurements in moving systems. These mathematical relations would become central to special relativity. But in Lorentz's interpretation, they still lived inside a framework where the ether could remain as a preferred background. This is a subtle historical point, but it gives the documentary depth. The same mathematics can sit inside different meanings. In one view, contraction helps explain why motion through ether is hidden. In another, contraction is part of the relationship between observers without needing an undetectable ether frame. The equations may resemble one another, but the story told about reality changes. This is why Einstein's later move was not simply technical, it was interpretive. It changed what the mathematics meant. It removed the need for a hidden stationary medium and treated the relativity principle and constancy of light as foundational. Lorentz had helped build part of the bridge. Einstein crossed it into a different conceptual country, but before crossing physics, lived for a time on the bridge. That in-between state is one of the richest parts of the story. The old ether had not fully disappeared. The new relativity had not yet reorganized everything. Scientists were working in a twilight of explanation, where successful formulas and uneasy interpretations stood together. A sleep documentary can linger here because the tension is quiet. There is no battle scene, no public collapse. There is only the mind trying to keep a world coherent, while one careful experiment keeps pulling at a loose thread. The Michelson-Morley result did not act alone. Around it were broader problems in electrodynamics, light, and moving bodies. Maxwell's equations had connected light with electromagnetic waves. Physicists were asking how the laws of electricity and magnetism should appear to observers in motion. They were asking whether the speed of light should depend on the motion of the source or the observer. They were asking whether there was one true frame of rest beneath all relative motion. The ether sat at the center of these questions because it seemed to offer that true rest. But the more important the ether became, the more troubling its undetectability became as well. If it was the preferred background of reality, why did experiments fail to reveal motion through it? If it governed light, why did light not betray its presence in the expected way? If it was physically real, why did it require increasingly careful protection from measurement? The attempt to save ether, therefore, prepared the mind to move beyond it, not because the rescue attempts were foolish, but because they clarified the stakes. Lorentz and others developed mathematical tools and conceptual insights that would remain important. Even when the old interpretation faded, parts of the structure survived. A theory under strain can still produce powerful ideas. This is one of the gentler lessons of scientific history. Progress does not always come from clean victories. Sometimes it comes from intelligent rescue attempts that almost work. A struggling theory forces sharper definitions. It makes hidden assumptions visible. It pushes scientists to ask what must be preserved and what can be released. The ether struggling to survive made physicists think more carefully about motion length time and light. That is why this middle stage matters so much. If we rush directly from Michelson-Morley to Einstein, we lose the texture of the transformation. The old worldview did not step aside politely. It defended itself with serious mathematics and careful reasoning. The absence of the ether wind did not immediately create relativity. It created a pressure field in which many minds worked. The question slowly changed. At first, the question was, can we detect the Earth's motion through ether? After the null result and the rescue attempts, a more troubling question emerged. Why does the attempt to detect that motion keep failing, even when the experiment is designed with great care? That second question is deeper. It does not merely ask where the ether wind is. It asks whether the idea of such a wind belongs to the right framework at all. It begins to suspect that the problem may not be measurement alone, but the assumption that there is a hidden absolute rest waiting to be found. Still, this shift did not happen in a single stroke. There were years of adjustment discussion and mathematical refinement. The ether remained useful in some formulations. Lorentz's ideas gave physicists ways to calculate and interpret. The old theory became more sophisticated, not simply weaker. Yet its sophistication came with a kind of unease. The ether had been saved, but it was becoming harder to say why it had to remain. This is the emotional shape of the section. The old invisible ocean lingers. It is defended, it is made subtler. It survives the missing wind by changing the rest of the world around it. But each change points towards something beyond the original picture. The rescue begins to look like preparation. A moving body contracts. Measurement depends on motion. The laws of electromagnetism demand deeper consistency. Light refuses to behave like an ordinary wave in an ordinary medium. The old ideas do not simply break. They bend until the next question becomes possible. And somewhere beyond that bending, Einstein's approach is waiting. It will not ask how to protect the ether from the missing fringe shift. It will ask what physics looks like if the speed of light is fundamental, and the laws of nature are the same for observers moving uniformly relative to one another. It will ask whether space and time themselves must be reconsidered. When that question arrives, the old ether will no longer stand at the center. For now, it remains in the story as a concept under strain. It remains as an ocean without a detectable wind, a medium protected by contraction, a hidden rest frame that experiment cannot easily reveal. It remains because science is patient with ideas that once made sense. It remains because the disappearance of a worldview is rarely immediate. But the burden has shifted. The ether is no longer simply carrying light. It is carrying the weight of its own concealment. That weight changed the emotional meaning of the ether. At first, it had been a hidden support. Later, it became a hidden problem. It was no longer simply the medium that made light possible. It was the thing that had to explain why its own motion relative to Earth could not be found. A hidden thing can remain scientifically useful if its effects are clear. But when its most expected effect disappears, hiddenness becomes more difficult to defend. The question becomes sharper. Is the ether hidden because our instruments are not good enough, or because the idea itself no longer belongs at the center? No single answer arrived instantly, but the direction of pressure was clear. The more physics tried to protect the ether, the more it had to rethink the things around it: matter length, motion, measurement, reference, frames. The rescue attempt was turning into a transformation of the whole neighborhood of ideas. This is why the Michelson-Morley experiment should not be imagined as a hammer blow. It was more like a carefully placed wedge. It entered a small gap between prediction and observation. Over time, that gap widened. The old framework did not explode, but it became harder to close around the result. By the time Einstein's work appeared, the question was ready to change. Not because everyone had abandoned the ether, not because the old view had no defenders, but because the conceptual landscape had been prepared. The missing wind, the contraction hypothesis, Lorentz's transformations, and the puzzles of electrodynamics had brought physics to the edge of a different way of thinking. The ether had been saved for a while, but the effort to save it had made another future visible. By the beginning of the 20th century, the ether had become difficult to defend in its older, simpler form. It had not vanished from scientific language. It still appeared in theories and habits of thought. Many physicists had been trained to imagine light as a wave needing a medium, and the ether had served that purpose for a long time. But after experiments like Michelson and Morley's, and after the increasingly subtle efforts to explain them, the ether no longer felt like an easy foundation. It had become something that needed protection. The original question had been natural. If light is a wave, what carries it? The ether answered that question in a familiar way. It made light resemble other waves. It gave space a hidden substance. It offered a medium beneath the visible world. But the attempt to detect motion through that medium had failed in a famous and careful way. The expected wind did not appear. Einstein entered a world already filled with this tension, but the history should be told carefully. He did not simply look at the Michelson-Morley experiment and invent relativity as a direct response. The problems were broader. They involved the behavior of light-electricity magnetism, moving observers, and the relationship between physical laws and different frames of motion. The ether was one part of a larger puzzle. Einstein's 1905 work on special relativity changed the situation, not by adding one more protection for the ether, but by changing the question. Instead of asking why motion through the ether could not be detected, he began from two principles. The laws of physics should have the same form for observers moving uniformly relative to one another, and the speed of light in vacuum should be the same for such observers, regardless of the motion of the light source. These statements are simple to hear, but their consequences are profound. To feel the depth of those consequences, imagine two observers moving steadily relative to one another. In ordinary intuition, each might disagree about speeds or directions, but both seem to share the same underlying time. They may see events differently, but somewhere behind their perspectives, common sense imagines one true clock and one true arrangement of space. Special relativity changes that. If both observers measure the same speed of light, then the old background cannot remain untouched. The measurements of distance and duration must adjust between observers. Time cannot simply be a universal river flowing identically for all. Length cannot simply be a property independent of motion. Simultaneity cannot be assumed without asking simultaneous for whom. These ideas are now familiar as phrases, but they remain strange in feeling. They ask the mind to give up a quiet assumption it rarely notices. We do not usually think of time as a measurement that depends on motion. We think of it as the stage on which motion occurs. We do not usually think of length as relational. We think of objects as having their lengths, whether anyone moves or not. Relativity did not erase ordinary experience. It revealed that ordinary experience is a limited guide. This is why the Michelson-Morley experiment fits so elegantly into the new world. The experiment had searched for motion relative to a hidden medium. But if the laws of physics are the same for uniformly moving observers, and if light's speed remains invariant, then the failure to detect an ether wind is no longer an awkward exception. It becomes natural within a framework where no such detectable preferred state of rest is required. The absence that troubled ether theory becomes expected in a deeper theory. If the speed of light remains the same for observers in uniform motion, then time and space cannot remain exactly as common sense imagines them. Measurements of length and duration depend on motion. Simultaneity, the idea that two events happen at the same time, becomes more delicate. The stable stage on which events seem to unfold begins to change. The old ether had tried to preserve a hidden background. Einstein's approach made that background unnecessary for the central physics. This did not make the universe easier to picture. In some ways, it made the universe stranger. The ether, for all its odd qualities, still belonged to a familiar pattern. Waves need a medium. Relativity asked people to loosen an even deeper intuition, the belief that space and time are absolute in the simple way daily life suggests. In ordinary experience, a minute feels like a minute for everyone. A ruler seems to have the same length, no matter who measures it. Two events that happen together seem simply together. Motion changes appearances, but beneath those appearances we tend to imagine a common clock and a common stage. Special relativity disturbed that confidence. It did not disturb it for ordinary walking speeds or daily rooms where Newtonian intuition remains extremely useful. It disturbed it at a deeper level where light becomes the guide. Light travels so fast and in such a fundamental way that it exposes limits in our ordinary concepts. It forces a rethinking of what observers in motion can agree upon. This is why Einstein's shift was larger than an explanation of one experiment. The Michelson-Morley result fit naturally into the new framework because a failure to detect motion through ether no longer needed the same kind of rescue. If no detectable ether rest frame is required, then the missing ether wind loses its old mystery. The experiment becomes one clue among several that the older question was not the final question. The light had not failed to speak. It had spoken against an assumption. This is one of the most important changes in the story. The same result can mean different things inside different theories. In 1887, the missing fringe shift was a difficulty for ether theory. Later, in the context of relativity, it could be seen as part of a broader movement away from absolute rest and toward a new understanding of light and motion. The fringes themselves did not change. The meaning brought to them changed. Einstein's power was partly his willingness to stop asking for a mechanical medium in the old sense. Instead of treating light as something that had to be carried by a hidden substance, he treated its speed and the symmetry of physical laws as fundamental. The center of explanation moved from medium to principle. This movement from medium to principle is one of the great intellectual turns in modern science. It means physics was becoming less dependent on a picture the mind could visualize mechanically. The question was no longer what substance is vibrating. It became what rules must measurements obey. That change can feel cold at first, as if a vivid image has been replaced by abstraction. But the abstraction carried a different kind of beauty. A mechanical ether gave the imagination something to picture. Relativity gave the intellect a structure that held together with extraordinary consistency. It did not satisfy the old desire for a material carrier, but it explained why the search for that carrier's wind had failed. This is often how science deepens. It does not always give us a clearer picture in the ordinary sense. Sometimes it gives us a more reliable structure at the cost of familiar imagery. The mind loses one kind of comfort and gains another kind of truth. The ether had been picture-like. Relativity was relational. This does not mean that images became useless. Scientists still use images, analogies, diagrams, and thought experiments. Einstein himself famously used thought experiments to explore physical ideas. But the images had to serve the principles, not replace them. They had to be disciplined by what the laws demanded. In that sense, the story of Michelson Morley is also the story of a change in scientific imagination. The old imagination pictured waves in a medium. The new imagination accepted that light might reveal something more fundamental about the relation between observers, clocks, rulers, and motion. It asked the mind to stop looking for the old ocean and begin listening to the rules that made the ocean unnecessary. This was not a small emotional change for science. The 19th century imagination often wanted hidden machinery. It wanted an underlying substance, a mechanism beneath appearances, something the mind could picture, even if the eyes could not see it. The ether gave light a kind of mechanical home. It made the emptiness of space feel filled. Relativity did not give back that comfort. It gave a deeper order instead. The laws became more important than the imagined medium. Space and time, once treated as the background of measurement, became part of what had to be understood. The world became less familiar, but more coherent. This is why the transition should not be told as a simple triumph over foolishness. The ether had been a serious idea. Lorentz's attempts to preserve it were mathematically and scientifically important. The contraction hypothesis, which began as a way to explain the missing ether wind, pointed toward the fact that length measurements might depend on motion. Even rescue attempts can contain the seeds of transformation. Science often advances through such layered paths. If framework meets difficulty, it is repaired. The repair becomes sophisticated. The repair reveals deeper assumptions. Then another way of thinking arrives and gives a different interpretation to tools that were developed inside the older view. Lorentz's mathematics did not disappear, but the meaning of the mathematics changed. In Einstein's hands, contraction and time dilation were no longer just effects that hid motion through ether. They became features of the relationship between observers in motion. The preferred ether frame was no longer needed to explain the measurements. What had been a protective mechanism became part of a new geometry of experience. This is a profound reorientation. The old question asked where the ether wind had gone. The new question asked how measurements of space and time must relate if light speed is invariant. The first question tried to detect motion through a medium. The second reshaped the meaning of motion itself. That is why Einstein belongs near the end of this documentary, not at the beginning. If he appears too early, the ether becomes merely a wrong idea waiting to be corrected. But after the listener has passed through the ether's appeal, Michelson's precision, the apparatus, the null result, and the attempts to save the old framework, Einstein's shift feels earned. We can feel why the question had to bend. The ether once seemed necessary. The machine was built to detect its wind. The expected effect did not appear. The theory was protected by increasingly subtle ideas. Then a new approach asked whether the hidden medium had been the wrong center of attention all along. The turn is quiet, but it is immense. The quietness of the turn matters. In popular memory, scientific revolutions are often told as dramatic breaks, as if one genius suddenly illuminates a dark room. But the reality is usually more gradual. Einstein's 1905 paper was radical, but it emerged in a world already prepared by Maxwell, Lorentz, Poincare, Michelson, Morley, and many others. The new theory did not appear from emptiness. It reorganized a field of existing problems. That is why the documentary should preserve the slowness of the story. The power of Einstein's shift is greater, not smaller, when we see what came before it. The ether had made sense. The experiment had been careful. The null result had been difficult. Lorentz had made serious efforts to save the framework. The stage was not one of ignorance replaced by brilliance, but of an old structure brought to its limits by its own refinement. Einstein's genius lay partly in recognizing that the rescue might not be the main task. Instead of asking how the old medium could be hidden, he asked what the laws of nature required if the principle of relativity and the constancy of light were taken seriously. That change allowed the same experimental difficulty to be understood without the old background. The missing ether wind no longer needed to be explained by a medium that refused to show itself. This did not make the universe less strange. It made the strangeness more exact. Time could dilate. Length could contract. Simultaneity could depend on motion. Energy and mass would eventually be seen in a new relationship. The old mechanical image was gone, but the new order was not vague. It was sharply structured and mathematically disciplined. This is the kind of mystery that modern physics often gives us, less picture, more precision. It is not a thunderclap. It is more like a change in the direction of thought. The problem no longer lies only in a missing experimental sign. It lies in the assumptions that made that sign seem necessary. The universe is not refusing to reveal the ether wind because the instrument is too weak. Perhaps the universe does not organize motion around such a wind. The room in Cleveland did not change. The stone did not change. The mirrors did not change. The mercury did not change. The fringe pattern was the same historical fact it had always been. But physics began to tell a different story about it. A machine built to catch the earth, moving through ether, became in memory a machine that helped show why that kind of motion might not be physically meaningful. The experiment did not lose importance when ether faded. It gained a new kind of importance. It became one of the places where an older expectation met the limits of its own language. This is how science sometimes moves from one world to another, not by throwing away every fact, but by changing the pattern in which facts belong. A result that once looked like a difficulty becomes a clue. A failed detection becomes evidence against the framework that demanded detection. A missing wind becomes part of a new understanding of light. Yet the new world asked for humility. It asked people to trust principles that led beyond ordinary intuition. It asked them to accept that daily experience, while valid in its own scale, does not reveal the deepest structure of motion. It asked them to let go of the idea that the universe must supply a mechanical image whenever the mind wants one. The ether had made the invisible feel material. Relativity made the material world feel deeper than visibility. This shift did not remove mystery. It relocated it. Instead of asking what invisible substance fills space, physicists were led toward questions about the relationship between observers, the constancy of light, and the structure of space-time. The mystery moved from the contents of space to the rules by which space and time are measured. For the listener, this can be felt gently rather than forced. Imagine the difference between asking what fills an empty room and asking what makes the room's measurements meaningful. The first question looks for a substance. The second question looks at the framework itself. Ether belonged to the first kind of question. Relativity opened the second. That is why the old ether became less necessary. It was not simply that physicists failed to find it. It was that a new framework could explain the relevant phenomena without needing it in the same role. Once that happened, the ether began to lose its central position. A concept that had once seemed required became optional, then increasingly historical. The disappearance of necessity is one of the quietest ways an idea fades. A theory does not always die because someone proves it impossible in every imaginable form. Sometimes it fades because the work it once did can be done better without it. The ether had carried light in imagination. Relativity allowed light to belong to a deeper structure of law. This is a different kind of ending for an idea, not humiliation but displacement. The ether had helped physics reach a certain point. It had guided questions, shaped experiments, and forced refinements. Then when the question changed, it stepped back into history. It remained important as part of the path, but no longer as the foundation. Michelson and Morley's experiment stands exactly at that crossing. It belongs to the old world because it searched for the ether wind. It belongs to the new world because its failure helped show why the old search was not enough. It is both an endpoint and a beginning, both a failed detection and a doorway into another physics. That is why the story still holds the imagination. That is a much stranger place for mystery to live. A hidden ocean can be imagined even if it cannot be seen. Space-time requires a more disciplined imagination. It asks us to accept that the measurements we treat as obvious are part of a deeper structure. It asks us to think of time not merely as a universal flow, but as something connected to motion and observation. This is why the Michelson-Morley experiment remains so compelling. It belongs to the history of an old question, but also to the birth of a new one. It shows the moment when a search for a medium became part of a larger reconsideration of reality. It does not carry the entire burden of relativity by itself, and it should not be made to. But it stands as one of the clearest signs that the older picture of light and motion could no longer remain untouched. The old question asked, where is the ether wind? The deeper question became, what does its absence teach us about the way nature measures motion? By changing that question, Einstein did not erase Michelson and Morley. He helped reveal the lasting meaning of their result. The experiment was no longer only a failed search. It became part of the path by which physics learned to stop looking for a hidden sea and begin rethinking the shorelines of space and time. And once that shift occurred, the final meaning of the experiment widened beyond ether. It became a story about scientific method itself, about how carefully measured disappointment can outlive the theory that first produced it, about how the universe sometimes answers a question by showing that the question was too small. The old question had asked for a wind. The result had offered a stillness. Now the stillness could be understood as evidence. The story of the Michelson-Morley experiment does not end in the basement. It continues in the way the basement was remembered. A room that once contained a careful optical apparatus, a floating stone, a bath of mercury, and 2 patient observers became something larger in scientific memory. It became a symbol of one of the most important lessons in experimentation. A result can change history, not because it finds what was expected, but because it fails to find it under conditions that matter. The experiment had searched for the ether wind. It had looked for the Earth's motion through an invisible medium that many physicists believed must exist if light was a wave. The instrument had been sharpened by precision and protected from disturbance. It had compared two paths of light while the apparatus slowly turned. If the old picture had been right in the expected way, the fringes should have shifted. They did not. The result lasted because it was not vague. It did not merely say that no one had seen ether. It said that a specific predicted effect sought by a specific method had not appeared. That made the absence disciplined. It belonged to an experiment precise enough to trouble theory. This is what gives a null result its power. A weak absence proves little. If one searches carelessly and finds nothing, the failure may belong to the search. If one lacks the right instrument, the missing result may only reflect human limitation. But if the conditions are strong enough, if the prediction is clear enough, and if the expected effect still does not appear, then the absence becomes information. It becomes a boundary. Boundaries in science are not always walls. Sometimes they are more like coastlines. They show where one way of thinking meets something it cannot cross without changing form. The Michelson-Morley result marked such a coastline for the old ether. The idea could still move along the shore, so to speak, through modifications and interpretations, but the direct route toward a detectable ether wind had become blocked. That boundary did not make inquiry smaller. It made it more honest. A good negative result removes false confidence. It does not tell scientists to stop thinking. It tells them to think differently. It shows that one expectation has failed, and by doing so, it protects the future from endless repetition of the same assumption. It narrows one path so that another can be noticed. This is why the experiment has a legacy beyond physics. In many fields, a strong negative result can be a gift, even if it first feels like disappointment. It can prevent a medical treatment from being trusted without evidence. It can show that a predicted particle is not present at a given energy. It can reveal that a correlation does not hold under better conditions. It can force researchers to revise models that had grown too comfortable. Science needs such refusals. Without them, theories would expand too easily. Every favored idea could survive by moving just beyond the reach of testing. Every failure could be dismissed as inconvenience. The discipline of experiment would weaken. A theory must risk something when it meets measurement, or the measurement has no power. Michelson and Morley made ether risk something. It tells science that one path is narrower than it seemed. It does not necessarily provide a new road at once. It does not always deliver a replacement theory, but it changes the map. It marks a region where expectation has met reality and failed to pass through. The Michelson-Morley experiment became one of the most famous examples of that kind of boundary. Its meaning did not arrive all at once. In its own time, it was part of a continuing struggle over light ether and motion. Later, after the development of special relativity, it came to be seen as a landmark in the fading of the old luminiferous ether. The same result gained depth as physics changed around it. That is one of the most interesting things about science. A measurement can wait for its meaning. This delayed meaning is one of the most restful and profound parts of the story. It suggests that science is not always aware of its own turning points while they happen. A result may be recorded carefully, discussed cautiously, and placed into the literature without anyone yet knowing how large its shadow will become. Only later does the shape appear. Looking backward, we can see the Michelson-Morley experiment as a landmark. But in its own time, it was part of a continuing conversation. This should make the story feel more human, not less. People rarely know when they are standing at the edge of a future transformation. They work with the concepts they have. They measure what they can. They interpret results with the tools available. History gives the event a clarity the moment itself did not possess. That is why humility belongs at the end of the documentary. Not only humility before nature, but humility before history. The meaning of a discovery, or of a failure to discover, may outgrow the people who first made it. Michelson and Morley asked a question about ether drift. Later, physics found in their answer a clue about the structure of reality. The experiment was smaller than its legacy, but it was careful enough to deserve that legacy. Not every fact arrives with the theory that will finally explain it. Sometimes an experiment records a difficulty before the right language exists. Sometimes the present can only say, "This does not fit," while the future discovers what the misfit was trying to reveal. The Michelson-Morley result belonged to that category. It was a careful fact whose significance grew over time. This makes the story quieter and more powerful than a simple tale of instant revolution. The experiment did not single-handedly create relativity. It did not prove every possible ether impossible. It did not make the scientific world change overnight. Its force came from a slower process. It placed pressure on an old idea, made rescue attempts necessary, and helped prepare a world in which a different question could be asked. That is how a careful negative result can shape knowledge. It does not always destroy a theory at once. It changes the conditions under which the theory can continue. It forces refinements. It exposes hidden assumptions. It makes scientists ask whether they are protecting an idea because it is still necessary or because it is familiar. The ether had once made sense of light by giving it a medium. After Michelson and Morley, that medium had to explain its own failure to appear in the expected way. The burden shifted from the experiment to the theory. The question was no longer simply whether the apparatus had found the ether wind. The question was why the theory had led people to expect a wind that the apparatus did not detect. This is a subtle but deep change. It moves science from disappointment towards self-examination. What did we assume? What did we ask? What did our analogy hide? Did we mistake the success of a picture for the truth of its underlying structure? The ether had been a powerful picture because it made light waves feel familiar. It connected the mystery of starlight to the everyday logic of waves in water and sound in air. But the universe is not required to preserve the comfort of an analogy. At some point, the analogy must meet measurement. In Cleveland it did, and it did not survive unchanged. The final legacy of the experiment is therefore not only about ether, it is about intellectual honesty. Michelson and Morley built a device to find a sign. When the sign did not appear, as predicted, the result had to be preserved, even though it did not satisfy the expectation that gave birth to the test. That preservation is at the heart of science. Not loyalty to a beautiful theory, not loyalty to a familiar picture, not loyalty to the answer one hoped to find, loyalty to the encounter between expectation and the world, loyalty to the measurement even when the measurement is inconvenient. This is why the story has a calming quality, despite its conceptual depth. The experiment does not move through violence or spectacle. It moves through patience. A beam of light divides. Mirrors return it. Fringes form. A stone platform turns. Observers look carefully. A predicted sign remains missing. And because it is missing carefully, it endures. From this endurance, the mind can widen outward. Scientific history is filled with such moments. An expected object is not found. A predicted effect fails to appear. A beloved treatment does not outperform a control. A theory that once seemed natural meets a measurement that refuses to cooperate. Each case must be interpreted cautiously, but the broader principle remains. Not finding something can be a discovery when the search is strong enough. The Michelson-Morley experiment teaches that absence can be active. It can guide. It can constrain. It can redirect attention. It can make an old explanation less easy and a new explanation more thinkable. It can clear space for a question that could not be heard while the old answer still seemed inevitable. This is why the result that refused to appear became one of the most famous results in science. The experiment's greatness lies not in spectacle, but in discipline. It did not give the world a new object to point at. It gave the world a missing effect that had to be explained. It turned non-appearance into a historical force. At the end, the story returns naturally to the basement. The journey has moved through wave theory, ether, precision, optical interference, the null result, the rescue of the old medium, and Einstein's reframing of light and motion. But the final image is still simple. A beam enters the instrument. It divides. One part travels one way, another at a right angle. Both return. The pattern forms. The stone turns gently on Mercury. The observers wait for the hidden current. The expected sign does not come. At the beginning, this was the problem. By the end, it has become the point. The experiment's lasting value lies in the fact that it did not force nature to speak the language scientists preferred. It arranged the question carefully and accepted the answer that came back. That answer was quiet. It did not say everything. It did not end all debate. It did not immediately produce the new theory. But it was enough to make the old certainty less certain. And sometimes that is where the deepest changes begin. Science is not only a collection of answers, it is also a way of becoming more honest about questions. Some questions are shaped by assumptions too hidden to notice. Some metaphors guide inquiry for a while, then begin to mislead. Some expected signs fail to appear because nature is organized differently from the picture we carried into the room. The only way to know is to ask carefully. Michelson and Morley asked carefully. Their experiment did not find the ether wind. Because it failed so precisely, it helped physics learn that the search itself had been shaped by an older understanding of light motion, space, and time. Nothing seemed to move. And from that stillness, a new way of imagining the universe became possible. The story also leaves us with a gentler thought about failure itself. In ordinary life, failure is often treated as the opposite of success. One tries to find something and does not find it. One asks for a result and does not receive it. The attempt seems incomplete. But the Michelson-Morley experiment shows a different kind of failure. It failed only if success meant finding the ether wind. It succeeded if success meant testing an expectation with enough care that the result could be trusted. It succeeded if success meant forcing theory to become more honest. It succeeded if success meant helping science move beyond a picture that had once seemed necessary. This is why the title of the documentary matters. The experiment should have failed in the sense that its intended search did not produce the intended sign. But it did not fail in the deeper sense. It became one of the most fruitful failures in scientific history. It showed that an experiment can miss the object it seeks and still strike the hidden assumption beneath it. That is a rare kind of success. The divided beam did not find the old ocean. The turning stone did not reveal the expected current. The fringes did not move as the theory required. Yet the experiment gave physics a fact that could not be comfortably forgotten. Sometimes the universe teaches by giving. Sometimes it teaches by withholding. In Cleveland, it withheld the wind, and in that withholding, it gave science a new direction. By the end of this story, the basement in Cleveland no longer feels like an ordinary room. It becomes a threshold between two ways of imagining the universe. On one side stood the older world where light seemed to need an invisible ocean, and where a precise enough instrument might reveal the earth moving through it. On the other side stood something quieter and stranger. A world where the missing signal mattered. A world where the failure of an expectation could unsettle old assumptions, invite new theories, and help prepare the mind for a deeper understanding of light motion, space, and time. The Michelson-Morley experiment did not announce a revolution in a single dramatic moment. Its importance grew slowly. It entered science not as a loud discovery, but as a careful refusal. The ether wind did not appear. The pattern did not shift as expected. And because the experiment was too careful to dismiss that result, had to be carried forward. There is something quietly beautiful in that. Science does not move only by finding new things. It also moves by learning where not to look, by discovering which assumptions cannot survive measurement, and by allowing a difficult question to remain open long enough for a better way of thinking to arrive. So, we return one last time to the divided beam of light, the mirrors, the floating stone, and the patient observers waiting for a movement that never came. Nothing seemed to move in the way they expected. And yet from that stillness, the shape of the universe began to change.